Hello everybody and welcome to today's lecture on clustering. I am Dr. Andrey Holz and we will be diving into one of the foundational unsupervised learning techniques used in machine learning. Clustering is everywhere, from customer segmentation in marketing to anomaly detection in cybersecurity. Today, we will cover key concepts, approaches, and best practices to ensure you have a deep understanding of this technique. This is our roadmap for the lecture. We will start with the basics to build strong foundation, move through various clustering approaches, and discuss practical considerations. By the end, you will explore advanced topics and best practices to help you navigate real-world clustering tasks. Let us start with the introduction. To position clustering within machine learning, let us review three main types. First, supervised learning uses labeled data to predict outcomes like identifying spam emails. Unsupervised learning, where clustering belongs, deals with unlabeled data. Here we aim to uncover hidden structures. And lastly, semi-supervised learning bridges the gap, combining small labeled datasets with larger unlabeled ones. Clustering is an unsupervised approach, and it's all about discovering patterns in chaos. However, there are options where we can use semi-supervised data to solve clustering. Let's start the introduction to clustering. Our goal for today is to understand what is clustering and what are the main types of clustering and how to deal with clustering on the real-world scenarios. Let us get started. And first of all, what is clustering? Clustering is the process of grouping data points based on their similarity. Unlike supervised learning, there are no labels to guide us, just the raw data. And for instance, clustering helps in customer segmentation, grouping similar customers for targeted marketing, or in anomaly detection, identifying usual behavior in a network. Mathematically, clustering aims to partition the dataset X into K clusters that are as compact and distinct as possible. Just like on the image, so we have unlabeled data, and then we have labels that we detected as clusters. To separate the data into meaningful clusters, we rely on various strategies. Distance-based methods like K-Means focus on proximity. Density-based methods such as DBSCAN identify dense regions and treat sparse points as outliers. Probability-based approaches assign probabilities for soft clustering. And for text or document clustering, similarity-based metrics like cosine similarity come into play. And in specialized fields, we can use domain-specific rules to guide clustering. And since I mentioned like distance-based clustering like K-means, distance measures are the foundation of clustering. They define how close or similar data points are, which directly impacts cluster formation. Euclidean distance is intuitive but sensitive to scale, so normalization is essential. And for grid-like or spatial data, Manhattan distance works well. Jacquard is great for binary data, like detecting overlaps in sets. Hamming is another choice for binary sequences, such as comparing genetic codes. When working with correlated features, Mahalanobis adjust for feature relationships, and cosine similarity excels with text data or sparse matrices. And as you might consider, well, there are a lot of types of clustering. Since there is no one-size-fits-all clustering algorithm, each type has strengths suited for specific tasks. Centroid-based methods like K-Means are fast and effective for spherical clusters. Hierarchical approaches excel in revealing nested structures. And density-based methods like DBSCAN handle arbitrary shapes and outliers. Graph-based techniques such as spectral clustering explore relationships, and fuzzy methods like FuzzyCMeans allow for soft boundaries. The choice depends on the data set and the problem you're solving. And this table shows the taxonomy of clustering algorithms. Note the diversity and methodologies. It is crucial to understand your data before choosing the right approach. And based on the table, can you suggest which algorithm might work with irregular shaped clusters with noise? So if you do, put it in the comment. And here we have a visual comparison of various clustering algorithms applied to different datasets. Each row represents a different dataset with unique shapes or characteristics, and each column shows how a particular algorithm performs on that dataset. And again, algorithm choice matters. The performance of each algorithm depends heavily on the shape and density of the data. And while K-means is fast and simple, it struggles with non-spherical clusters. DBSCAN and HDBSCAN, hierarchical DBSCAN, are excellent for arbitrary shapes and noise handling, but parameter tuning can be tricky. Spectral clustering and Gaussian mixtures are more flexible but computationally intensive. And dataset characteristics drive the selection. Always analyze your data before choosing an algorithm. If you have prior knowledge about shapes, density, or overlapping, use it to guide your choice. This slide beautifully illustrates that no single clustering algorithm is universally perfect, and the art of clustering lies in understanding your data and leveraging the algorithm best suited to reveal its hidden structures. And well, this slide contrasts two major approaches for clustering: hard clustering and soft clustering, using K-means and, for this example, Gaussian mixture models. So clustering methods can broadly be categorized into hard and soft. K-means on the left is hard clustering. It forces every point to belong to exact one cluster. And this is simple and effective for non-overlapping clusters, but fails when clusters overlap or have noise. On the right, Gaussian mixture models show soft clustering. Here, points are assigned probabilities of belonging to each cluster. And this approach better reflects reality, where boundaries between clusters are often fuzzy. For example, imagine you're segmenting customers, and hard clustering approach might classify each customer as high spender or budget cautious. But soft clustering acknowledges that some customers exhibit traits of both categories. The choice between hard and soft clustering depends on your data and the problem you're solving. Which approach do you think would be better for applications like medical diagnosis or image segmentation. And let us move on. And K-means is one of the most popular clustering algorithms due to its simplicity and speed. It minimizes the within cluster sum of squares, WCSS, aiming to make clusters compact. The process involves initializing centroids, assigning points, updating centroids, and repeating until convergence. However, it has limitations. Poor initialization can lead to suboptimal results, and it struggles with non-spherical clusters. To address these, techniques like K-Means++ helps initialize centroids more effectively. And the equation at the bottom shows this metric, the within cluster sum of squares. Basically, it tries to make each cluster as tight as possible. By the way, why do you think K-means struggles with overlapping clusters? Any ideas on how we might overcome this? Let us break down the K-means algorithm into its key steps, focusing on how it iteratively refines clusters. By the way, this illustration shows step by step the process of clustering. So, the first step is initialization. We start by randomly choosing k centroids. These are the central points around which clusters will form, and on this image they are like black crosses. Keep in mind, random initialization can affect the results, so techniques like K-means++ are often used to improve this step. And the second step is assignment. Each data point is assigned to the nearest centroid based on a distance metric, typically Euclidean distance. And this step involves division the data into k initial clusters. The third step is update. Once the points are assigned, we update the centroids by taking the mean of all the points in each cluster. This ensures the centroid move closer to the actual cluster center. And convergence check. The algorithm iterates between assigning points and updating centroids until convergence. This means either the centroids stop moving significantly or we hit a maximum number of iterations. On the plot, you can see how the algorithm works visually. And starting with random centroids, each step adjusts the cluster boundaries and refines the centroids to minimize the within cluster sum of squares. And think of this process like organizing a classroom. Initially, students might sit randomly, but over time, they naturally group within their friends, refining their position. By the way, why do you think poor initialization might lead to poor clustering results? Can you suggest how we might handle this issue? K-means is one of the most popular clustering algorithms, as I said, and it is for a good reason. And let us discuss why it is so widely used, as well as where it might struggle. First of all, strengths. It is simple. It's easy to implement, easy to understand. It is accessible for everybody. It is scalable. Its time complexity scales linearly with the number of data points, so it's kind of efficient moderately large datasets. And for low-dimensional data and a small number of clusters, K-means is incredibly fast, outperforming more complex algorithms. As for the limitations, well, it is sensitive to initialization. Poorly chosen initial centroids can lead to suboptimal clusters and require more iterations to converge. And K-means assumes clusters are spherical and evenly sized. If your data has irregular or overlapping clusters, this assumption breaks down. And also, you have to specify the number of clusters in advance, which isn't always straightforward. And techniques like elbow method can help estimate this, but it's not always a great choice. And high dimensional data increases the cost of distance calculations. Reprocessing steps like dimensionality reduction can mitigate this. And let's look at the complexity breakdown. The total complexity depends on the number of points, dimensions, clusters, and iterations. While the algorithm typically converges quickly, poor initialization or high dimensionality can increase it, making it computationally expensive. And in summary, K-means is a fantastic tool for well-separated clusters and low-dimensional data. But for irregularity, but for irregularly shaped clusters or complex data sets, you might need alternative methods. Another clustering approach is hierarchical clustering, and it is unique in a way. It does not require a predefined number of clusters. Instead, it builds a dendrogram, a tree-like structure that shows how clusters are formed. Agglomerative methods start small, merging points, while divisive methods start with one large cluster and split. The choice of linkage, single, complete, average, or words method determines how distances between clusters are measured, and this affects the resulting cluster shapes. And dendrogram is a powerful visualization. You can cut it at any level to extract clusters, and this offers flexibility. However, it becomes computationally expensive for large datasets. And let us look at how agglomerative clustering works. By the way, this visualization shows how it works. At start, each data point is treated as its own individual cluster. Think of it as having every student in a classroom sitting alone. Then there is a merging step. In each iteration, the two closest clusters are identified based on a chosen linkage criterion. So single linkage is the minimum distance between points in two clusters. Complete linkage is the maximum distance between points in two clusters. Average linkage is the average distance, and worst method that minimizes the variance within clusters after merging. And these two clusters are merged into a single cluster once we have selected them. And the step is visualized on the right. Yeah. And update step. After merging, the distance between the newly formed clusters and the remaining clusters are recalculated. And the step updates how the algorithm gets like the cluster closeness and the repeat stage. So the process continues until all data points are merged into one giant cluster or until a desired number of clusters is achieved. The result is often visualized as a dendrogram, showing how clusters are merged at each step. And in the plot, you can see like the hierarchical clustering in action. And initially, every point is its own cluster, and as the algorithm processes, the clusters merge based on like chosen linkage criterion. Agglomerative clustering has some powerful advantages, but also notable limitations, especially as dataset size increases. Let us discuss these in details, starting with the strengths. So, strengths. No predefined clusters. One of the biggest advantages of hierarchical clustering is that you do not need to predefine the number of clusters. Instead, just use the dendrogram. Dendrogram visualization, it provides a clear hierarchical structure showing how data points merge into clusters step by step. And this is a fantastic tool for understanding relationships in the data. Unlike flat clustering approaches like K-Means, hierarchical clustering can identify nested clusters. For example, in customer segmentation, you might find subgroups within a larger cluster, offering deeper insights. And you can customize the algorithm by choosing different linkage criteria such as single, complete, average, or words methods. And it handles irregular or elongated cluster shapes effectively, making it suitable for datasets with complex structures. And what about limitations? Well, another clustering approach is hierarchical clustering, and it is unique, high computational cost. The biggest drawback of agglomerative clustering is its computational cost. And you can take a look at the table just to understand it. And it is also sensitive to outliers. Outliers can distort the merging process. Since the algorithm cannot revise decisions, an outlier might force unrelated points into the same cluster. And as I mentioned, irreversible merges. Once two clusters are merged, the decision cannot be undone. And again, the curse of dimensionality, high dimensional data increases the computational cost. And although the dendrogram provides insights, it is very subjective. It is useful, yes, but deciding where to cut it can be subjective and require additional validation metrics. And you can take a look at the complexity table. The total complexity is cubical, and it makes hierarchical clustering impractical for very large datasets. Well, optimized implementation exists, and they can reduce the complexity of a single linkage, but scalability remains a concern for dense or high-dimensional data. Another method is DBSCAN, or density-based spatial clustering of applications with noise. DBSCAN is density-based, and it works exceptionally well for dataset with noise and irregularly shaped clusters. It relies on two parameters, epsilon, which defines the neighborhood size, and mean points, the minimum number of points to form a dense region. Core points form the backbone of clusters, border points connect clusters, and noise points are left unclustered. This makes DBSCAN great, but tuning epsilon and mean points is crucial for good results. And the diagram illustrates how DBSCAN separates dense regions while isolating outliers and identifying border objects. Notice how noise points, like point N, aren't assigned to any cluster. And given the advantages and limitations, Where do you think DBSCAN would outperform K-means or hierarchical clustering? As for the algorithm steps, let us dive into the working DBSCAN. Unlike K-means or hierarchical clustering, it defines clusters based on the density of the data points, making it powerful for identifying shapes and separating noise. The first step is neighborhood identification. The algorithm starts by identifying the epsilon neighborhood for each point. This is the set of all points that lie within a distance epsilon of a given point. Core point detection. A point is labeled as a core point if its epsilon neighborhood contains at least mean points, the minimum number of points required to form a dense region. Core points act as the anchors for forming clusters. And in the plot, these core points are highlighted, and you can see them. Cluster formation, the next step. Starting from an unvisited core point, DBSCAN recursively aggregates all density reachable points to form a cluster. A point is density reachable if it can be reached from a core point by moving through other core points. And outlier identification. Points that cannot be reached from any core point are labeled as noise or outliers. These points remain unclustered and provide additional insights into the data. The plot on the right shows the detection of core points, which are backbone of clusters. And notice how DBSCAN doesn't force every point into a cluster. It naturally separates noise from meaningful clusters. What about strengths and limitations? DBSCAN has several advantages over other clustering algorithms, but it also comes with its own set of limitations. So, strengths. No need to predefine cluster counts. It automatically detects the number of clusters based on density, which is a huge advantage over like K-means. It handles hard shapes. Yeah, unlike K-means, which assumes spherical clusters, DBSCAN can detect clusters of any shape, such as rings or elongated structures. And robust to noise and outliers, it explicitly identifies noise points, separating them from datasets. And minimal parameters. You only need to specify two parameters, epsilon and mean points. What about limitations? Well, issues with varying densities. It struggles when clusters have significantly different densities, as the same epsilon and mean points may not work well for all clusters. And it is sensitive to parameter selection. The choice of epsilon and mean points is critical, and poor parameter selection can lead to either too many outliers or merged clusters. As for the high dimensionality, its performance decreases in high dimensional space due to the course of dimensionality, where distance metrics become less meaningful. And as for the border points, they may belong to multiple clusters, leading to non-deterministic results. And the table on the right shows the complexity of different steps. In low-dimensional data, special indexes can improve the efficiency to n log n, but as dimensions increase, the complexity may rise to quadratic O n squared. FuzzyCMeans is a flexible clustering algorithm that allows data points to belong to multiple clusters. That's a soft clustering. This is particularly useful when clusters overlap or when we're uncertain about strict assignments. The algorithm assigns a membership score to each point, indicating how strongly it belongs to a cluster. And by adjusting the fuzzy parameter m, we can control the level of overlap. It's computationally intensive, but it is super valuable for applications like image segmentation or pattern recognition. And the membership matrix W holds the probabilities of each point belonging to each cluster. Imagine it as a heat map of a relationship between data points and clusters. FuzzyCMeans clustering is a soft clustering algorithm. It allows each data point to belong to multiple clusters with varying degrees of membership. Let us break down it into the steps. The first step is the initialization. First, we define the number of clusters, the fuzziness parameter, and the stopping criteria. The fuzziness parameter controls how soft the boundaries between clusters are. The higher values of m allow more overlap. Next, we initialize the membership matrix W, where each element represents the membership degree of point E in cluster J. The key here is that the sum of membership across all clusters for any data point is equal to 1. And then the step is centroid calculation. For each cluster J, we calculate the centroid as the weighted mean of all data points. And the membership degrees act as weights, giving more influence to points with higher membership in the cluster. And then we have an update step, the membership update step. The algorithm updates the membership degrees based on the distance of each point to all cluster centroids. A point closer to a centroid has a higher membership degree in that cluster. This formula ensures the degrees reflect the relative distance. And the next step is convergence check. The algorithm checks if the changes in membership degrees or centroids are below a predefined threshold. If so, it stops. Otherwise, it repeats steps 2 and 3 and 4. The plot on the right visualizes FuzzyCMeans in action. Notice how the data points have different shades of color representing their membership degrees in multiple clusters. This overlapping nature makes FuzzyCMeans ideal for datasets where boundaries are ambiguous. What about strengths and limitations? Well, it is a soft clustering, and unlike hard clustering methods like K-means, FuzzyCMeans allows overlap, making it more realistic for applications where boundaries are not clear-cut. Flexibility. It works well with uncertain or ambiguous cluster boundaries, such as when analyzing customer preferences or medical diagnosis. And practical applications. So FuzzyCMeans is particularly effective in image segmentation, where pixels often belong to multiple regions, and pattern recognition where overlapping patterns are common. What about limitations? So it is computationally intensive. The algorithm is slower than K-means as it requires updating both membership degrees and centroids at each iteration. This can be a bottleneck for large datasets. And it is initialization sensitive. The results depends on the initial placement of cluster centroids. Similar to K-means and poor initialization, it can lead to suboptimal clusters, not to global optimal ones. And it is parameter sensitive, so So choosing the fuzziness parameter and the number of clusters requires careful tuning. Incorrect values can lead to meaningless clusters. Noise impact this type of clustering. It is sensitive to noise and outliers. Even distant points contribute to cluster centroids, potentially distorting results. And if you take a look at the complexity, this increases significantly for large or high dimensional data sets. If you take a look at the calculations, if you take a look at the formula. This slide summarizes the key clustering algorithms we have discussed, comparing their types, strengths, and limitations. And let us review each algorithm and consider when you might use it. So the K-means. K-means is simple. K-means is simple, scalable, and efficient for large data sets in the specific implementations like parallelized implementation or mini-batch implementation. It works well when clusters are spherical and evenly distributed. On the other hand, it requires specifying the number of clusters in advance, which can be challenging. It's also sensitive to initialization and struggles with outliers, as these can distort clusters' boundaries. It is ideal for quick and scalable analysis when cluster shapes are straightforward. What about hierarchical? So hierarchical does not need to predefine K. The dendrogram provides a clear visualization of nested clusters, making it suitable for exploratory analysis. On the other hand, it is computationally intensive, especially for large data sets. And it is good for small data sets where understanding hierarchical relationships is critical. As for DBSCAN, it is great at finding hard shapes, and it does not require the number of clusters, making it flexible. On the other hand, it struggles with clusters of varying densities and requires careful tuning of epsilon and minimum points. It is useful for datasets with noise or irregularly shaped clusters, like geographical data or anomaly detection. And there are also other clusters. You can take a look at them, but I'll mention the ones that we covered. So FuzzyCMeans, the process that handles overlapping clusters through soft assignments, which is more realistic in certain applications. And it is computationally intensive and is sensitive to initial memberships and number of clusters. It can also be affected by noise. It is suitable for problems with unclear boundaries, such as image segmentation or medical data analysis. What about clustering evaluation? So how to evaluate them? Well, there are two groups of metrics, internal and external. Internal means we do not have the labels. And internal metrics like silhouette, score, assesses how well points fit within clusters, or like within cluster sum of squares, evaluates compactness. The Davies-Bouldin index penalizes clusters that are too close to each other, while Calinski-Harabasz index rewards well-separated clusters. These metrics helps us judge the quality of our clustering results objectively. And notice how each metric addresses a different aspect of clustering, compactness, separations, or both. And this is the metrics if we do not have the labels. What if we, for some reason, do have the labels? Maybe somebody labeled them. So it is like evaluating clustering results is essential to understanding how well our algorithm performed. External metrics compare the clustering outcome to ground truth labels, which are available in benchmark datasets, but in practice they might not be available. So what about the metrics? So RAND index, it measures the proportion of correct pairwise decisions, meaning how often pair of points are correctly grouped together or correctly kept apart. It is useful for datasets where the focus is on pairwise relationship. And there is an adjusted version of this index. The adjustment makes it more robust for random agreements. And it helps remove the bias introduced by random cluster assignments, especially in datasets with many classes. Another metric is normalized mutual information, the mutual dependence between cluster assignments and true labels normalized to fall between 0 and 1. And a value of 1 indicates perfect correlation, while 0 indicates no correlation. It is ideal when measuring how well the structure of clusters aligns with the true labels, regardless of cluster size. V measure, it balances two aspects of clustering quality, the homogeneity and the completeness. So homogeneity, all points in a cluster belong to the same class. And completeness, all points of a class are assigned to the same cluster. And it computes the harmonic mean to give the overall score. It ranges between 0 and 1, and the use case is a balanced metric for evaluating both inter-cluster consistency and inter-cluster separation. And these metrics give different perspective on clustering quality, and choosing the right one depends on your dataset and goals. For example, use ARI or NMI if randomness or class imbalance is a concern. Use V-measure when you need to keep homogeneity and completeness both. If you just need a simple pairwise evaluation, then you can go with the RAND index. Let us have some practical considerations in clustering. Choosing the number of clusters can be tricky. It is one of the most critical steps in clustering. There are several common methods to do so. The first one is elbow method. You can see it on the screen. So just plot the within cluster sum of squares against different values of number of clusters. And look for the elbow where the rate of decrease sharply slows down. This is where adding more cluster does not significantly improve compactness. In the graph, the elbow is at 5. This is the optimal number. Use domain knowledge. Analyze the dataset context and use natural grouping to determine K. For example, if clustering customers, domain knowledge might suggest that there are specific segments like high spenders, budget cautious, and so on. And use other metrics like silhouette, Davies-Bouldin, Calinski-Harabasz. These metrics evaluate the quality of clustering in different K values. So silhouette score can measure how similar points are within the clusters compared to other clusters. And the two other metrics also provide some insights. And select the K value where the metrics are optimal. And one of the ways also is to use dendrogram. So no single method is perfect, and use combination of these techniques to cross-validate the choice of K, ensuring it aligns with both data-driven metrics and your domain expertise. And like if you need to handle high-dimensional data, Just keep in mind the curse of dimensionality and the increased computational complexity for the clustering. And if you have to reduce dimensionality, use PCA, TSNE, UMAP, or use feature selection. And these techniques not only improve computational efficiency, but also enhance clustering performance by mitigating the challenges of high dimensional data. And again, scaling is crucial in clustering to ensure that features contribute equally to distance calculations. Without scaling, features with larger ranges can dominate for the clustering process, skewing the results. And by scaling, we prevent features with large values from dominating. And outliers and noise can significantly impact clusters by skewing centroids and distorting cluster shapes. When working with large datasets, efficiency and scalability becomes essential. Keep in mind that you should always look at the algorithm complexity, understand time and space complexness, and choose algorithm that scale with data volume. If you have large datasets, you can use data sampling. Just pick a sample of the data and work with it before you're starting to work with a huge dataset. And incremental clustering is also a nice choice. It updates clusters as new data arrived. Otherwise, the most of the clustering algorithms require you to train the model from scratch once you have the new data, and utilize parallel processing where possible. And if we're talking about like initialization step, poor initialization can lead to suboptimal clustering results and longer convergence times. How to deal with this? Use methods like KMeans++ and other methods to spread the initial centroids more evenly to improve speed and accuracy. This minimizes the risk of starting with centroids that are too close or poorly placed. Run algorithms several times with different initializations and pick the best results. Smart initialization and multiple restarts are simple ways to significantly improve your clustering results without changing the algorithm itself. Let's have some coding and we'll take a look at the demo. Okay, let us take a look at the clustering. So this will be simple, nice and smooth. Clustering is in scikit-learn.cluster. We will use K-Means, MiniBatch K-Means, DBSCAN, and agglomerative clustering. We will also use fuzzy clustering from scikit-fuzz. So let's get started. And we will define internal metrics, calculations, silhouette score, Calinski, Davies, and external metrics calculation, ARI, NMI, and we'll also calculate this sum of squares, look at the data, visualize the data, and this is our main function. We can run it, generate the data. Yep. So if we take a closer look, that's quite interesting since K-Means is showing some strange results. However, that is expectable due to its nature. And as for the FuzzyCMeans, as for the FuzzyCMeans, it works pretty well. So is the agglomerative clustering. If we take a look at the metrics here, we can spot that there are interesting clustering mechanisms. Thank you very much. Welcome back. And we have advanced topics and best practices on this. Now that we have covered the basics of clustering, let us dive into more advanced techniques that can handle complex scenarios and enhance clustering effectiveness. What if you need to handle mixed data types? In real-world datasets, you often encounter both categorical and numerical data. You can use go versus distance. It measures the similarity between mixed data types, making it ideal. Or you can use k-prototypes. It extends k-means by combining numerical and categorical distance metrics. And another advanced technique or advanced task that you might consider is preprocessing. Clustering isn't just for grouping, it can serve as powerful preprocessing tool. You can have it as a part of the anomaly detection pipeline. It can identify outliers that do not fit into any cluster. You can have it as a data compression, just summarize large data sets into representative clusters, reducing complexity. And you can have it as a feature engineering part. Use cluster memberships as new features for supervised learning, adding a layer of abstraction on your model. Again, model will benefit from integrating domain knowledge into it. What about semi-supervised clustering? Yes, you can do it, you can use it as a validation, or there are specific algorithms that can work with semi-supervised clustering. What about the feature selection and all the things around it? Well, use it. That's a great choice to reduce the complexity. Automate the process of fine-tuning for better results. Use grid search or randomized grid search or optuna or hyperopt to find the best hyperparameters automatically. This saves time and ensures your clustering algorithm is optimized for your dataset. You can also interpret clustering results. The value of clustering lies in its interpretation. So one of the ways is to use cluster profiling. You can analyze the characteristics of each cluster by looking at feature distributions. You can use techniques like silhouette plots, PCA, TSNE, UMAP, or dendrograms to understand and communicate the structure of your clusters. And of course, you can use statistical analysis, just perform hypothesis testing to confirm significant differences between clusters. And these advanced techniques make clustering more adaptable to complex and real-world datasets. Whether you're handling mixed data, optimizing hyperparameters, or using clustering as a part of a larger workflow, these methods allow you to push beyond the basics and achieve actionable insights. As we wrap up our discussion on clustering, let us review the key best practices to ensure your clustering efforts are effective and meaningful. First of all is understand your data. The first and the most crucial step is to really know your data. Analyze distributions, identify feature types, understand inherited structures before you select algorithm. Without this foundation, your clustering will lack relevance. Preprocess effectively. So data preparation is everything. Apply feature scaling, handle missing values, reduce dimensionality if necessary. Remember, clustering relies heavily on distance metrics, so your features need to be on a comparable scales. Choose the right algorithms. Match the algorithm to your data. Think about the size, the shape, noise levels, and what you're trying to achieve. For example, use DBSCAN for noisy data or KMeans for well-separated spherical clusters. And tune hyperparameters. Do not settle for default settings. Use methods like grid search or optimization techniques to find the best configuration for your algorithm. Validate and interpret. Always evaluate the quality of your clusters using appropriate metrics like silhouette score or external metrics if you have labeled data. Then interpret the clusters in the context of your application. Clustering is only as valuable as its real-world insights. And clustering is not just about finding groups, it's about discovering patterns and structures. So, and as a keynotes for this whole lecture, we have learned that clustering is great unsupervised learning technique with its application in many domains. We covered its types, algorithms, and the role of distance metrics. We also explored evaluation methods to assess clustering quality and determine the number of clusters. Finally, we discussed practical considerations and real-world applications, emphasizing how clustering simplifies and organizes complex data for better decision-making. Clustering groups data by similarity without requiring labels, making it useful technique. Hard clustering strictly assigns points to one group, while soft clustering allows overlap. Distance metrics define similarity and directly impact results. In evaluating clusters ensures quality, and pre-processing is key to fair comparisons. From customer segmentation to anomaly detection, clustering is widely applicable across domains. Think of this summary as a checklist. Each point reflects a crucial aspect of successful clustering. And as we conclude today's lecture, I want to leave you with this thought. Clustering isn't just a machine learning tool. It's a way to uncover the hidden stories within your data. Every dataset you encounter is a puzzle, and clustering helps you piece it together, whether it's finding new customer groups, detecting fraud, or discovering unknown patterns in scientific research. Clustering gives you the power to reveal the unseen. Remember, data is only as valuable as the insights you can extract from it. Clustering challenges us to think critically, explore creatively, and always push the boundaries of what is possible. As future data scientists or mathematicians and engineers, you hold the key to solving some of the world's biggest problems. Clustering, like all machine learning, is a tool that amplifies your creativity and analytical skills. So take these concepts, practice them, and don't be afraid to experiment. Every great discovery starts with curiosity. And I noticed a lot of curious minds. Go find the patterns, create clusters, and most importantly, trust the power of your own insights. Thank you very much for your attention and have a good day.